Good morning, good afternoon. Welcome to this Xendee webinar series today. We want to feature Mainspring's linear generators. And if you move to the next slideshow, please. My name is Michael Stadler. I'm the CTO and co-founder of Xendee, and I'm guiding you to this webinar today. Before we started Xendee, I was a researcher at Lawrence Berkeley National Laboratory. And parts of the technology that we're using in Xendee actually going back to that time. But I'm very excited today to have Shah with me here. He's a staff sales engineer at Mainspring, and he's going to talk about the technical specifications of the Mainspring technology, but also about the use cases. And Shah, maybe you want to introduce yourself a little bit here.
Great, definitely, Michael. Thank you so much. Thank you for providing us with the platform and the time to engage with the audience today. So for those that do not know me, my name is Shalal Mohammed. I go by Shah. I'm a staff sales engineer for Mainspring. I've been with the company for about 10 months now. As the name entails, the title entails, being sales engineer, we support our account executives all the way from pre-sales until contracting projects. And we also do in Mainspring, we do offer EPC services. So as a part of that, those tasks, I do solutioning, scoping, estimation of our EPC projects. Prior to Mainspring, I was in Cummins for about 10 years. So I do have extensive background within the power generation industry. Half of my career was focused on linear natural gas genset, which there's drawing some parallel between a linear generator and linear natural gas genset. So very happy to be here. Michael, I'll just turn it back over to you.
Yep. Can you move to the next slide, please?
Sure.
So before we jump into Shah's presentation, a little bit about Xendee, because maybe not everyone is familiar with us. We are a software/engineering company out of San Diego, California. And we really help our clients on the journey from designing projects to really implementing and controlling those projects, right? And we have multiple products here which help you through this process. The first one is the Discover tool, which is really a multi-site analysis tool, which helps us to screen multiple sites. If you are, let's say, a real estate owner and you have hundreds of sites, or you want to figure out in your portfolio what sites are really attractive for microgrids or DRs, then this is the tool that really helps you. With the proposal tool, you really can write proposals for funding agencies, government, or for your clients if you're a vendor very quickly. It's very database driven. You can do this within a couple of minutes. And then there's Design, which is our detailed techno-economic engineering tool, which not only allows you to assess the economics of microgrids and distributed energy resources, but also more electrical engineering problems like power flow and distribution system modeling. And then there's finally Operate, which we are going to release next week to the public. It's a microgrid control system, which actually helps you to control these technologies in the same way like you have been planning for. And for our Propose and Design tool, we offer our clients to put their technologies in a database. And we have multiple vendors in our database, and we just decided to also add Mainspring certified data in our database to help you and our clients with the modeling tasks. And by the way, we are the only software tool which has the certified Mainspring data in the catalog. Shah, can you jump to the next slide, please? So just very briefly before we jump into Shah's presentation, we have a lot of use cases that we can model in Xendee, from improving the cost, reducing the carbon emissions, increasing the resiliency. Of course, this cable and transformer sizing and loss calculation, which you see on the right-hand side here. We have here a very distributed microgrid system. We call this multi-node project, and you can really model the energy flow between the buildings and how this will impact cables and transformers. And of course, there's also electric vehicle modeling besides other use cases that we can do. But now I want to jump really into Shah's presentation. He will talk a little bit about some use cases and how Mainspring can help you. So Shah, please continue.
Thank you very much, Michael. Appreciate it, and we're very, very honored, very happy to be a part of your platform. Obviously, it's a very sophisticated when it comes to modeling system. So again, welcome everyone. So on the Mainspring side of the presentation, we're going to break the presentation down into two sections. The first section is going to be an overview of the company and of the product high level. And then the second part of the second section of the presentation is going to be a deep dive into the technical aspect of our linear generator. So for those that are technical savvy, just hold on to your seat. We'll get there, and we'll get the details of the equipment unfolded to you. So first thing first, what is Mainspring? So Mainspring it was originally founded by 3 Stanford engineers back in 2010. They were tasked to go out and research an affordable, reliable, and clean power source. So the research actually led them to the innovation of what we call today a linear generator. Fast forward to today, we have a proven commercial product that has been installed across multiple Fortune 500 customers and leading utilities. Obviously, all of this is possible because of a great team and talented and diverse team that Mainspring has. The folks that work within Mainspring have decade-long experience within the clean tech and the energy sector. And this is also backed up by investors that are forward-thinking, that have been investing in the clean tech and clean energy throughout their portfolios. And everybody shares the same vision here: clean, affordable, and reliable power. So with that being said, what do we offer within Mainspring? We offer 2 things, obviously. So first, we offer a product, and then we offer some services along with it. The product is a 250 kW linear generator that is scalable. So you can have a 250 kW linear generator on site, or you can have 25 megawatt, you can have 250 megawatt. You just need to scale them up, add as many units as you want. This is packaged inside an ISO standard ISO container, so it's relatively easy to install. It is fuel flexible. This is very important, and we'll take a big dive into how are we able to achieve this fuel flexibility. But it's fuel flexible, and it's very important to know that it's fuel flexible without retrofit. So you can put in any gaseous fuel into the system will operate, whether it's ammonia, whether it's natural gas, whether it's hydrogen. It will operate without any pre-notification to it. It is resilient. So the linear generator can run in parallel with utility. And in case of a utility outage, it can run in island mode. So it has the operational flexibility. Easy to permit because the way that the linear generator generates power, it is clean due to the low temperature reaction that we do versus combustion that other technologies do. So we have near zero emission, especially the NOx, which is very closely monitored by EPA. Again, as I mentioned, it's very easy to install because the listed product is inside an ISO container, roughly as big as a parking spot, so 20 feet by 8.5. In terms of the services, every single project we sell or every single package we sell, there's an O&M contract that goes along with it. We'll talk about how well we're doing in terms of reliability and maintenance. But on top of that, we actually have an analytic team, both in the country and overseas, that are monitoring the package 24/7. So this helps us to beat the NERC rate, availability rate to date. And the most recent statistic that was communicated to me was roughly about 80% to 90% of the issues that arise with the package are actually remotely troubleshooted. So we don't need to dispatch somebody to the site. And the good thing is, if something happens and the unit is down and cannot be troubleshooted remotely, we actually will dispatch somebody because we have we're very closely monitoring the operations of these units. Also, we do have the financing capability through our partner Nextera. So you don't have the cash purchase capability, or you'd like just to do an ESA agreement, you could actually go ahead and we'll partner Nextera with you to go ahead and do the financing for this. And all of this will be done through our account executive, so you don't necessarily need to talk to multiple different people. As I mentioned in the beginning of the call, we do also offer EPC, engineering, procurement, construction. So when we sell a package, we can also sell the EPC service with it. So we can actually go ahead, install it, connect the gas, connect the electrical, get the interconnection permit with the utility in place, get the PTO, and just turn the keys over to you. So it's going to be a full turnkey solution where the customer does not necessarily have to worry about anything. And we have that entire capability within our house. And then last but not least, if you're interested in alternative fuels, we can definitely help you with fuel supply support, get you with the right partner to move forward with that aspect. What does a linear generator what are the problems that the linear generator can solve for? Well, linear generator can typically solve for these for use cases. These are not the only use cases that linear generator can solve for, but typically this is what the customers have approached us with. And we've noticed no matter what the customer is, whether they're a data center, whether they're a landfill, whether they're a grocery store, a cold storage, they typically have very similar, this is the common denominator between them, very similar problems. And they'll rank these problems in different orientation, obviously depending on their priorities. But typically what we come across is a cost issue. A lot of customers are dealing with increased utility cost due to the infrastructure getting old, investment that utilities are putting in. So constantly that utility rate is going up. So basically, because of our capability to run in prime, a linear generator can be installed on site, run continuously, offset as much as possible from a utility point of view, while you still have the utility. So run in parallel with the utility, you still have the benefit of resiliency of the utility, but you are offsetting the cost as much as possible. And this is only possible because we can be permitted to run prime. Not every technology can do this. The other use case that we usually solve for, because of our lower low emission profile, near zero NOx, well, we can help the customer get this sustainability goal faster. A lot of customers do have 2030, 2050 goals. We can actually help them get there faster because our emissions is much lower. Resiliency, thanks to the capability of this unit to run both in prime or in parallel with the utility and to run in Allen mode, it can be switched over easily. And customers would like to have an asset that's not necessarily stranded to only one operation mode. Last but not least is speed to power. A lot of customers wants power now, but the utility cannot get that capacity to them. So a good example for these are the EV chargers across the country that they want power now in certain areas that typically are remote or typically very congested. The utility cannot get the power to them. They approach us to go ahead and install a linear generator on their site and be there for the duration until the utility is able to provide the power to them. And when the utility is there, we can switch the operation mode. So let's say we're running to charge the station, and then when the utility is there, the linear generator can then switch over to be a peak shaver. It can switch over to be backup. It can switch over to a cost analysis or a cost mitigation where it's running continuous and offsetting as much utility cost as possible. So that's what really achieves us. This whole fuel flexibility and operational flexibility gives us the ultimate flexibility. This is why a linear generator really stands out in the market. Nobody can do this today besides a linear generator. And that's purely because of the fuel flexibility. I talked about how we're fuel flexible. The linear generator is fuel flexible without any retrofit. So you put in any gaseous fuel into this system, it will adapt to it. It's called adaptive pressure cycle. Basically, it will figure out where the fuel is and automatically, autonomously, it will operate. There's no interruption in power. Again, we'll talk about in the details how are we able to achieve that in the technical slides. And then the bottom of this slide talks about that operational flexibility that I just talked about. So the first use case here is a speed to power, where the unit is running in Allen mode by itself, providing power to the site because we have load tracking capability. And then when the utility gets the site, we can switch that over to peak shaving. We can switch that over to potentially backup, whatever the customer requires. So reality on the ground is we get compared to other technologies. It's very important to know that linear generator is a new category of power generation. There's really no apple-to-apple comparison between us and any other technology. There's a sweet spot for us, but in the end of the day, customers are given this option. So this is the options that they deal with. It's important to understand what are the pros and cons of it. If you look at it, when you're looking at a scalability point of view, we do really have the scalability. It's one product, and it can be scaled as many units as you want, which in some products, you may not get that flexibility. And it's modular in a sense. We've talked about the fuel agnostic without retrofit. We really are the only product out there that can do that. We claim we're fuel agnostic and we don't need to do any retrofit. Low emissions, because the way that we generate the power is generated inside the power cylinder of a linear generator is low temperature reaction. Again, we'll talk about in a technical slide. The emissions are super low. It's actually, the linear generator is being permitted in the stringent part of the country, the South Coast. And we, in certain areas in the country, we're even air permit exempt. So there's no need to go through the air permit cycle in a sense. Able to start up ramp quickly. This is due to the fact that the units are, they can get up to speed, start quick, and accept low track. And then last but not least is the low total cost of ownership. There's three aspects that feed into it. It is the efficiency that we have, then the low maintenance cost, high reliability, low maintenance cost, and also the CapEx. So all of these three combined actually give us the best total cost of ownership in the industry altogether. So that's kind of high-level overview of the company and of the product. So the next set of slides are going to be a bit technical, and hopefully we can address some of the questions that you already may have about our product. So a linear generator is composed of two cores. That's what you see here is a core. This is really just simply what it is. This is just a linear generator right here. Obviously, we have balance of plants, which every other equipment does. We have an exhaust system, which is simply a tuned system. And we do also have an air intake with an air booster and so forth, piping. But really, the rest of it is just, this is the crux of our units. That's why it's called a core. There are two cores, as I mentioned, inside a single linear generator package. So that ISO container 20 feet by 8.5 has two of these. Each one produces roughly about 125 kW. So and combined together, they produce 250. So let's talk about what are the major components on this core. First one is a power cylinder, where the reaction zone, we call the reaction zone, that's where the reaction takes place. Then moving over is a linear electromagnetic machine, abbreviated to LEM. That's what we usually use, LEM. I'm glad we do use that abbreviation because I usually struggle with it. But LEM is simply the alternative of our system. So those are familiar with other traditional technology. This is where we produce power, we generate power. Next, we have air springs. So these air springs are simply just springs that store air, excess energy in form of air from the reaction, and then they provide the bounce back energy to the translator to push for the next cycle. Then those two things, those two pistons that are moving back and forth are called translator. We've previously have used oscillator, so you may still hear us use the terms interchangeably, translator, oscillator, but really translator is the term that we use now. And those just kind of move back and forth to generate power. And then last but not least, one very important enabling feature to our technology are the air bearings, which we'll spend a slide on this later on. But air bearings, in a nutshell, they're just simply air hockey table wrapped around the translators. They provide high-speed air as air as the cushion for the translator to move through. So one thing that you may notice now, this system is extremely simple. From if you compare us to, if you compare a linear generator to let's say an engine or a combustion turbine or some other technologies, this is a very simple technology. You just have a power cylinder in the reaction zone where all the action takes place. There's a direct translation of a linear motion into electricity, so that increases the efficiency. And you just have air springs that are potentially can never fail. I mean, they're just air, and there's plenty of it to supplement. So what we're going to do now, we're going to take out a zoom out effect and talk about each components separately to see what's happening there. So first thing, the power cylinder, the reaction. How does this reaction take place? I was talking to a couple of people earlier, and they're like, well, this looks like an engine. You're still doing compression and expansion. And you're right. I mean, that's exactly the concept. It's still a compression and expansion. But we're doing it differently because in an engine, there's combustion and flame involved. In our case, it's flameless, low temperature reaction, which are all those terms mean actually something major. And I'll talk about it in a second here. So let's just talk about the concept for a second. So the concept tells us every time you're compressing a fuel and air mixture inside a confined space, that air and fuel mixture will get to a point where either it reacts or it combusts, or you're inducing the combustion, as it would be in case of a spark ignited engine. Then there will be a point where at the moment when that reaction happens or that combustion happens, there's excess energy available in terms of heat. And then it pushes back on whatever it was pushing in the first place. So in case of an engine, it's a piston. In case of our case, it's a translator. It's pushing it back. It gets to the point where it has retracted well enough where exhaust ports are exposed, as it would be in our case, or valves are opening, exhaust valves are opening in case of an engine, right? And the cycle starts over again. So as I mentioned, we're very inherently different than an engine. And how is that so? Is because at point A, we're introducing a fuel and air mixture. Again, it could be any gaseous state, as I stated. It could be ammonia, it could be natural gas, hydrogen, whatever it is. So mix it with air, put it into the power cylinder. And then we're compressing this air and fuel mixture. What happens is that the ammonia, in this case, as it's the ammonia NH3 and O2, they're moving around, hitting each other fast. So this increases the temperature and pressure inside the power cylinder. Well, it gets to the point where they're moving so fast and they're hitting each other so fast, temperature has increased so much, the pressure has increased, there will be a moment where these bonds of the fuel and air will break and they will restructure themselves. Well, when they restructure themselves, they restructure at a lower state of energy. So you technically have excess energy available in the environment, in that particular environment. So that's how you see it from point B to C, you start to see the expansion backward. And this is a controlled reaction. So we know exactly when this reaction happens and we control it. So we control temperature and we control pressure inside the cylinder. And this is how we're able to achieve the low NOx, because we have a homogeneous, low temperature, flameless reaction. It happens equally all over the place. There's no flame involved and it's homogeneous. So you don't have any spots. And why homogeneous is important? Because in case of an engine, for example, if you have combustion, the way that combustion works, it expands out. So you have a spot where the spark happens or the combustion happens and it just expands out. Well, that spot right there actually starts to create a lot of NOx. But in our case, because it's homogeneous and is low temperature and it is a reaction, little traces of NOx are produced, almost close to zero, near zero. And then as that reaction has happened now, the low temperature reaction happened, it exerts a net zero force out on the translator. Translators are getting pushed out. We're taking electricity out in that case, and the cycle starts over again. So I hope that was clear from a concept, what happens inside the power cylinder or the reaction zone. So now let's move on to the next major component, which is the LEM, the linear electromagnetic machine. You probably know why I struggle with not spelling the whole thing out. I just call it LEM. Basically, what I show you here is only half of a core. So if you think of the animation a couple slides back, a full core has the reaction zone in the middle, 2 LEMs, and then 2 air springs, but I'm showing half just to get the point across. So the reaction is on the right, reaction cylinder is on the right, and then you have the air springs on the left. In Faraday, in electricity, we have a law that's called the Faraday law. Basically, Faraday law tells us that every time you have a moving magnet inside a coil of wire, you're inducing electricity or you're generating electricity. And that's exactly what we're doing. What a LEM is just a coil of wires, and we have magnets stationed on the translator within the portion of that, within confined space of that LEM. So every time those magnets, every time the translator is moving back and forth because of the reaction and the air springs, those magnets are moving back and forth with it. So if you look at the lower left, I'll do an animation of this from an electrical point of view. As the magnets are moving back and forth, we have just generated electricity. But if you're an electrical engineer, or even if you're not, you probably recognize this. This is not a pure sine wave in a sense. It's not something we recognize with what we are accustomed from an electricity point of view. Well, that's because, first of all, the system is a 12 Hertz system. Second, it is tapered off from the beginning and end because the magnets are actually in a complete stop when the reaction happens. They speed up. It gets to the middle where it's at high speed and then slow down again because of the air spring toward the very end. So you have this kind of interesting waveform with tapered off from the beginning and end. And then obviously that waveform repeats itself again. Well, we just generated a waveform that is technically not something we can use on a day-to-day life. So we need to do something with this, right? And what we know best in electrical engineering is when you're dealing with something that is not, you're not familiar with it or you cannot use it, let's just convert that to something where we can use it. And we do that best with AC to DC, DC back to AC conversion. Well, what do you see here on the top part of this slide is that we have this waveform that's 12 Hertz. That's not really something we can use today. We convert that to a DC bus where we have capacitors and batteries as well to maintain certain voltages. And then we convert that into an everyday use of 480, 60 Hertz that we're familiar with. Well, what did we just did here? We actually just pushed ourselves into an inverter-based technology. So that's why when we're dealing with the outside world, there's a lot of education involved, because we're painted with an engine because of that certain way that compression and expansion, but it's not really an engine. And then we're also painted as a solar battery because of our inverter base. But really, you probably get the point now why it's a new category of power generation. And what you see here, it's an inverter that is off the shelf. It's actually a Dynapower inverter here that we used. And it has the certification that every other inverter out there has, that is widely accepted, approved by utilities and by the permitting agencies. We have the UL 1741 SV, the IEEE 1547 inverter, and the package has the UL 2200. So the output of the spec of our equipment is a 480 three-phase, three-wire system. And again, just a simple inverter that we use out there. So we've talked about the reaction zone. We've talked about the LEM. We understand now, you should technically understand how the system is generating power. But I made a claim earlier saying that we have the lowest total cost of ownership because of our high reliability, low maintenance cost. And a major attribute of our low maintenance cost is because of the air bearings. As I mentioned, the air bearings are simply air hockey tables wrapped around the translators. So basically, translators are sitting on cushion of air. So if you look at the lower left picture, you see when the air is on, the translator are elevated in the middle perfectly with air surrounding it. And when air is off, it's sitting. Well, when the system is operational, we're pushing compressed air through that system. So those translators are moving back and forth on a cushion of air. Nothing is hitting each other. We're technically is enabling the zero contact operation, which increases reliability. And at the same time, we don't have any oil in the system, so that actually reduces the maintenance cost. So that altogether, given it's a really simple system, given it's really three major parts, given that we have these air bearings that enable this zero contact, altogether it makes a machine that is very high reliability, long maintenance interval, obviously, or low maintenance, and then it has a very high life expectancy, roughly about 20 years. Sorry, just one thing about this slide. So the elimination of oil also increases the efficiency. Why? Because if you look at a traditional engine, the system to manage airflow. So you have turbos that push the air through. You have valves that are opening. Because of the valves, you have certain other equipment, and then you also have oil pump that pumps pumps oil into the system. These are all auxiliary load, so they actually take away from the system capability. Again, this air bearings actually increases the efficiency for us. First of all, the reaction itself is a low temperature reaction, so we don't need to take heat away from the system. This is an air cooled system. This is not a liquid cooled system. So we don't need to deal with a lot of heat taken away. And also our system, we don't have any valves. It's just slots open from an intake air and exhaust air. And also we don't have any oil. So this entire auxiliary load, so if you look at an engine, literally half of it, or probably more than half, 60% of it is just auxiliary load to manage these, the oil and the airflow and so forth. We don't have any of those issues. That's why, again, these air bearings are actually a huge attribute of our technology. So one question that may come to you now is, if the air bearings are so great, why is it not widely used? Well, the air bearings have a low bearing load. They technically take about 1,000 Newton. And again, if you go back to the translator design, the translator is hollow cylinder. They're very light material. Really, the only weight on them is the magnets, which technically help with the electromagnetic force. It kind of helps elevate that too. But it's such a light metal, so it can move back and forth on a cushion of air. If you look at a traditional engine, the connecting rods where it connects to the crankshaft, that itself, just that point, experiences roughly about 100,000 newtons, 100,000 Newton of force. So that's why air bearings are very intrinsic to our design. It's not only the air bearing itself, it's actually how we design the entire system of the translator. And I apologize, the slide, I'm missing a couple points here. And the air bearings, the air, where does the air come from? Well, it comes from the air springs. We have plenty of it because that air spring is always charged. In every cycle, you have that air spring charge, and we're just supplementing the air in the system through the air spring, which we have plenty of it. You could never run out of air, and thank goodness it's free, so you don't have to pay for it. Okay, so fuel flexibility, another major attribute of ours. I pointed out in a couple points across the slides today. And let's just talk about it. How does it work? We do have something that's called adaptive pressure cycle, which I alluded to it earlier in the slide. Basically, before I even get into this, it's important to know that every fuel has a different reaction point. So natural gas, just for illustrative purposes, natural gas may react here, while hydrogen may react here, while ammonia needs to be compressed all the way to react here, right? So that tells you that the compression ratio for every single fuel has to be different. If you look at a traditional engine, you have a fixed structure. It's mechanically all tied together. That crankshaft has a certain turn radius, and it's not going to change its compression ratio. You have to physically change the equipment itself. So when you're building an engine or other technologies, you're building it for a certain fuel. In a fuel cell, as an example, the media is built for a certain fuel. In an engine, is built for a certain fuel. But ours, we don't really care, as long as you put a gaseous state in it, because we have a varying compression. The translator is light, and because of there's a direct connection between the translator and the LAM, we can actually drive the system to be faster or slower. So think of it as an AV car. When you're going uphill, you're drawing energy from the battery and you're putting it into the motor. So you're actually speeding up the system. So you're kind of doing work that way. But when you're going downhill, you're braking. That brake is actually being exerted by drawing power from the motor. So you're actually drawing power into the motors and charging the batteries. And it's simple. It's a similar concept here. So when we want the oscillators to be at a certain position, we can control the position exactly through the LAM. So we can either draw power and say, okay, slow down, or we can push power into the LAM and say, okay, translators, be faster or be at a certain position. And that software control compression helps us, because we can then, if you put in a hydrogen, we know exactly where hydrogen reacts, and we can stop right there. We don't need to push any further, because the moment you start to push further, you're actually working against yourself. You're decreasing your efficiency and you're derating yourself quite a bit. That's why you see it in engines. When you change the fuel, it could be, for example, a 2 megawatt engine. All of a sudden, it's like sub megawatt, because you're working against yourself for that particular fuel. But in our case, that's not the case. Where you put in that fuel, we know the system automatically realizes that, because it's light material, it realizes that it's pushing against itself now. Well, the next cycle, it adapts itself. It is software control. So we can say, okay, for hydrogen, you should be reacting here. For the natural gas, you should be going this far. For ammonia, you should be going this far, right? So it automatically understands that, automatically adjusts itself. That's why it is fuel flexible without any performance derate. There's obviously a slight change when the system is figuring itself out, probably a cycle or 2 cycle. But in grand scheme of things, that's nothing, because from an electrical output point of view, which that's what we care about, because we're generating power, there's zero disturbances, because we have a DC bus. So we're rectifying, we have a pure power quality going out of that inverter. And we can do any of these fuel that you have on the screen, as long as a gaseous fuel, you can go ahead and put it in the system. The system would automatically figure it out and be able to adapt to it. And you can do a blend of them. You don't necessarily need to just change the fuel. We only have one point of connection when it comes to the fuel. The blending has to be done outside, or the change has to be done outside, but you don't need to notify the system. You can just go about business and change the fuel on the fly. All right, so because of the controls on the system, we have a lot of capability to perform in different modes. Obviously, that has enabled us to operate in 2 modes, in grid parallel mode and in grid forming mode. When we're connected to utility, we can sync into the utility voltage and frequency and supply the system. And because this is an inverter-based technology, the inverter actually does that. So when you look at an engine, you need to have a paralleling breaker. You need to have sensing both on the utility side and the generator side, or the load side, generator side. You need to sync. The generator needs to drive into that, close the breaker, and then go about business. Well, in an inverter case, it picks up that and immediately changes the output based on whatever the frequency and voltage requirement is. So there is that fast capability when it comes to grid paralleling. And in case of an outage, when an outage happens, having adequate balance of plant, site balance of plant in place, we can go ahead and start outputting power. One thing to note is that the reason why we can operate in Allen mode and some other technologies cannot is because of our load tracking capability. So we can load track and determine what the load on the system, what the requirement of the system is, and output the power that way. So this is an example where it's a 230 kW unit in a site that is 280 kW. Well, the unit is going to be load tracking all the way up to 230, the maximum capacity of the unit, and then the rest will be supplemented by the utility. So you're offsetting as much as possible from a utility point of view, then the rest will be supplemented by the utility. And this is not necessarily the case with certain other technologies, because some of them like to run in baseload. They don't like to modulate their output. Some other technologies may be just slower to respond when it comes to load. We do have batteries on our DC bus, so any major step we can take it. We can take technically 100% step load on these units without really any major disturbances that would be outside of the ISO guidelines. So emissions. We talked about how we have low emissions because of the low temperature reaction within our power cylinder or reaction cylinder. But if you compare us to other technologies, we have technically one of the lowest technologies, lowest profile out there. And this is for natural gas and for hydrogen. So this is the final slide here, just ending it with a case study. This particular customer has ended up having a fleet of EV trucks without really any EV charging system. So they ended up approaching the utility. The utility said that they don't really have the power available to them. So they approached us to provide the on-site power. So this was a speed to power case, use case, where we provided 3 megawatt of linear generator. They do also have, this is a microgrid, they have 6 megawatt of battery storage on site. So the linear generators are actually running continuously. So they are charging the batteries when the site is not in use, when the EV chargers are not in use, and they support the EV charging station when the system is peaking. Well, this has so this saved the customer about 2 years of time. Otherwise, they would have just had to wait on standby for the utilities. And as some of us are familiar with the utility world, sometimes they said, 2 years down the road, it may be extended out, and nothing against them. It's just the nature of the business and of the supply chain. So even though they were promised 36 months, we were able to reduce that down to 12 months, get power to them on time. And when utility gets the site, as we talked about this power operation flexibility, we can change our mode of operation. We can, at that point, drive the cost of the utility down as much as possible by running continuous, or we can play backup, or we can play peak shaving. That's all the operation flexibility that's available to us. And this site is actually operational now. Customer is very happy with the operation. We were very happy and very proud to be a part of this project. So that gets me to the end of the slides. Michael, anything else to add to the presentation here?
No, it's very exciting, and I mean, I really it's a cool technology, and you did a great job in explaining it. So thank you for this. So let me just go here for a couple of questions here. Let me start. So there's one question from Bill asking if the unit can be grid forming when connected to the utility, not just islanded mode.
Yes, it can be. Sorry, the question was, can it run in grid following, not only in island mode?
Can the unit be grid forming when connected to the utility, not just islanded mode? So can it basically switch back and forth? I think that's what the question is.
Yeah. I think if you're running in grid paralleling and there's an outage, you can switch over to grid forming mode and back and forth. That can be done via Modbus, so it could be dry contact or hardwire connection to our control box, and you can switch back that over the way that you want it.
Okay. Another one is, do you know if your linear generator will qualify under section 48E in 2025? So I'm not sure what this means, but maybe you guys know what section 48E means. Maybe someone can explain it.
I don't, and I'll rely on my team members to see if that brings any bubble for them.
Okay. Maybe Ali, at the questions from you, maybe you have some more details, or we'll follow up with you later on this. So I have one question also. It almost sounded like, Shah, you can do fuel switching during operation, as you made the explanation. I think that's really, I mean, if I understand it correctly, I think that's a key point here, right? Because you just can do this on the fly.
Yes.
Yeah.
So it's seamless. The word that the terms are used is seamless operation, right? So you can change them right on the fly. Obviously, as I mentioned, there's one point of connection from a gas point of view. So we don't do the blending or the changing within our system. So whatever the fuel that comes in, we'll operate on it regardless.
Yeah. Another clarifying question. You mentioned low temperature, and if you can speak about this, I'm not sure if you can, but what does low temperature actually mean? I mean,
yeah. So in I guess in the traditional terms, what I was told, low temperature means anything below, roughly about 800 C or 500 C is considered as low temperature. From what I was told in the engine world, because of the combustion, the flame, having a flame present, you actually go into almost 1200 C, and that creates a lot of 1200 to 1500 C. That creates a lot of NOx because of that.
Okay, thank you. Another question from Mark here: for natural gas input, what are the CO2 emissions? I think it relates because you were talking a lot about NOx. So maybe you can point a little bit to the CO2 emissions here, right?
I don't have the exact details of the CO2, like what's the exact limit. But one thing I wanted to point out is that NOx is such a closely monitored gas constituent by the EPA. And that is typically the hardest to deal with in an engine, because the engine creates it, and what we're mostly familiar with is the engine. The engine creates it, there's a lot of it, and really the only way to deal with it is outside. So when it gets to the exhaust and you introduce an SCR system, selective catalytic reduction, in a lean burn natural gas genset, because those get permitted to run in continuous and prime. And that system itself introduced a lot of issues, right, with having NOx, because the third-party equipment, and you have urea consumption, you have maintenance consumption, you have commissioning issues. Sometimes it may not even pass test. So that's the NOx, why we put so much focus on NOx. On the CO, even though it's created, as a matter of fact, CO is in the air, so you can never eliminate it altogether, no matter what your technology is. But CO gets treated much easier because you have OxyCat. OxyCat is relatively simple product, proven product in the market. They're smaller in size, and we actually do have an OxyCat on our system, so it reduces the CO quite a bit to permittable level. But again, we don't really put too much focus on CO just because it's addressable. It can be corrected, especially with the fuel source. If you put in the right fuel source, you don't really get carbon out. But the NOx is a huge point for us because it's just nobody else can do it.
Yeah, got it. Thank you. And Ali clarified what he meant with Section 48E. It's for the ITC elective pay qualification 2025. And Microgrids are only qualified this year. So he's asking if Mainspring know if this technology will be qualified for this ITC elective pay beyond 2025. So maybe you don't know this right away. Maybe we have to follow up.
I don't. I know that ITC, we are qualified now, and that's a major push for our customers to actually get orders in this year. But I'm not familiar with this exact section, so we'll have to probably get back to that.
Yep. Okay. Man, there are a lot of questions piling up. So let me see. One question I had was regarding maintenance. I mean, can you actually, because it sounded like you can run multiple technologies in parallel in a box. Can you perform maintenance while one side is running and or not? I mean, would be cool, I guess.
That is a pretty cool feature of ours, actually. You can turn one side down. So since there are two cores in there, I just pointed forward, but since there are two cores in there, you can actually turn one core down and perform maintenance on the other one. It is in the works. I know it's going to come out. I'm not sure, to be honest, if it's out yet 100% or if it's going to be out soon, but that's one aspect we're going to drive it. So you only reduce your system by half. So it's not only a modular system. You can take as many 250 kW. It's actually modular even inside the equipment. So you can technically lose only 125 kW of your power.
Great. I have already seen a couple of questions regarding the purchase costs, and also Wisdom from Mainspring answered them, but there's another one so that everyone can hear them maybe. What's a purchase cost comparison compared to backup generation on diesel or also fuel cells? So maybe you can give some indication in where you stand here if you want to do that.
Yeah, I think I'll just let Wissam and the rest sales folks answer that question. I'll tackle the technical questions. I'm not sure if Wissam's on the call.
Yeah, I'm on Shah, and the answer is $2,500 to $3,000 per kilowatt, depending on number of units.
Thank you. Okay, so that's done. There's so many questions. I'm sorry that I'm jumping topics here, but they're really piling up. Yeah. What's the startup? So Richard is asking, what is start time from cold start? Demand response time required is 7 minutes. So the question probably is if you're fast enough to do a cold start and do demand response.
Yeah, I think we are. And actually, this is a relatively fast start compared to some other technologies. It's not a diesel engine with 10-second start, but it would roughly come up to rated speed, voltage, and frequency within 5 minutes from a very cold start. But if there's a change of mode, we can do that in somewhere between 10 seconds to 30 seconds. But from a cold start is about roughly 4 to 5 minutes, and I think that even can be pushed down further. It's currently in R&D to push that further. One aspect we're driving toward is to see if in the future we can be NFPA 110. I know that we're not certified for that, but we're pushing to have the start time meet that requirement or get as close as possible.
Okay, thanks. I found another question. So it's from Brad, and he's asking when the modeling of your generator will be available in Xendee. And it's already available. We already brought the technologies online in the Xendee platform, and you can use it if you have a license, or we are happy to really do some modeling for you guys if you're overwhelmed with projects.
And Michael, just one point. I was a Xendee user in my past life, so I don't want to necessarily market it, but I really like Xendee. I had used other platforms too, and I think one thing that's really important for us, that's intrinsic to our product, and also is a huge capability of Xendee, is being able to model different fuels over a duration of time, right? So we're talking about this fuel flexibility. A lot of our customers are interested because they don't want their asset to be stranded after certain years, right? Policies change, fuel supply chain, all of that changes. And our fuel flexibility is a major win for customers, especially those ones that are trying to switch over to clean fuels when it becomes more available. And I think being able to model that, like for the first few years, you're going to run in natural gas, as in case of Prologis, actually. It is running natural gas, but they're expecting to run, there are multiple publications about this, but they're expecting to run hydrogen in the future. So being able to model that and understand the system payback and system financing cost and behavior, I think that's a major point for Xendee and our partnership.
Yep. I saw a couple of other Xendee questions. I will get back to this, but Ken is asking if there's any D rating that you guys consider depending on the elevation and cold climates or hot climates. So is there also an impact of salt on the engine?
So D rates, yeah. So we do account for altitude and temperature D rates. That's just physics. You can't really get away from it. But from our point of view, every project we do modeling with it, like financial modeling internally. And for the financial modeling, we do load durations and so forth, and D rates are accounted for it. And as every other companies out there, technology company out there, we will communicate the D rates, what they will be once we have an MOU signed with you guys and our project on hand.
Okay, so I have one question which I was thinking during your presentation. So, this is a very cool technology, but what other technologies you see in combination with your linear generator, right? A lot of people are thinking about PV systems, batteries. So, what's a very typical project you're seeing? You talked about Prologis, which we also know from our projects, but where do you see a benefit in combination with other technologies? I think that's my question.
Yeah, so we do see one of the use cases that as a matter of fact, one of the first projects that were installed was solar firming. A lot of customers that are quote unquote forward thinking, that are thinking of this clean energy and clean power, it actually matches with our vision and mission, right? Clean, affordable power. So they couple that with our system. So whether it's a battery, a solar, or wind, they can couple that with our system because our system is technically clean, dispatchable, curtail as low track, be able to operate both in parallel and Allen mode. So all of those are attributes that you don't typically see in a clean source technology or generators, right? So solar is not dispatchable, wind is not dispatchable, battery is dispatchable with short duration. So really we come in as the, fill in the gap or check all the boxes there, right? So it's a clean technology. It can firm the solar, it can firm the wind, or it can charge the batteries. And that's kind of where we typically see ourselves coupled. But granted, we don't only really participate there. We have, projects that are potentially going to be coupling our units with combustion turbines. I mean, that's the customer just wanted the cleaner, more modular. They went to us, but they already had combustion turbine on site. So we're even coupling with there. So we don't necessarily have yay or nay in a sense, but we can, because electricity wise, we can parallel with anybody, with anyone, as long as we have adequate controls and so forth. But typically we see the solar and battery.
Okay, thanks. I'm really having troubles keeping up here with the questions. A market-related question from Jason. Will you be offering your linear generator in Australia too?
Currently, it's only offered in the US. We are actually looking into expanding internationally. I'm not sure of the plans. Probably will be a few years down the road. But again, I don't know of all the plans, but it's currently just offered in the US.
Okay. So there's another question about the lead time for product supply and wisdom. I think I have seen you already answering this in the channel, so maybe you want to repeat this for the rest of us. What is the delivery lead time for product supply? Is one question here.
So typically about 9 months.
Yeah.
For the product to be delivered to site, the lead time.
Okay. Okay. Yeah. Another question related to Xendee Mainspring. So it seems like we triggered a lot of interest here, and Ryan is asking if we are going to show at some point how to model the Mainspring in Xendee. So we didn't do it in this webinar because we were thinking about the technology, but we can take this back and offer this for some interested people on how to model Mainspring technologies in Xendee. So we can certainly do that. So this is done here. What else? Okay. We already did this. Okay. Is the 44% efficiency relative to the fuel combustion potential of the fuel? I'm not really sure what this means. So 44% efficiency seems good compared to an internal combustion engine, where approximately half of the energy goes to waste heat. So maybe it's also related to waste heat capture. So I'm not sure where you guys stand on this.
Yeah, so we don't really offer CHP in a sense. We don't capture the heat because it's a low grade, low temperature heat. It's not high grade as you would see in an engine. Mm-hmm. That's why we have such a high efficiency, 45%. And by the way, that's electrical efficiency, not efficiency side equipment.
Oh, okay.
So again, yeah, we don't really have much heat to capture. There's still some, I think roughly about 90 kW, 100 kW, something like that, usable. But I don't think you can use that for steam. It's probably just for hot water. Don't really see a CHP as a huge application for us.
Okay. Another question here is, how heavy are your linear generator boxes, and can they be easily moved around? Because I got the impression that you come in when the grid is not readily available, like with Prologis, and you kind of getting boxed in or shipped in. So can you really be easily moved to other sites here?
The package itself is about 20 tons, so 40-something thousand pounds. We don't have a unit that's certified mobile off highway where it's on the on a trailer. I mean, we have it for testing purposes, but nothing that is certified. And it kind of goes back to the fact that customers would like to have this. This is such a future-proof asset that you don't really move it around as much. I mean, it's a fuel flexible, and once you install it on site, it can operate on any fuel. It can operate on propane. It can operate on hydrogen. So customers usually just look for the long term. And this is not an engine that's overhauled. So you don't die, or the unit does not die after 8 years, or you need to do a major overhaul, it will run for the 20 years. So usually it's a stationary application.
Okay, okay. And there's a question from Robert, which ties into this maintenance. So what are the maintenance intervals for you guys, actually, if you can speak to this?
The only consumable really for our system, major consumable, are potentially rings that are on the piston. So you need to maintain, as I talked about, maintain pressure and temperature inside the reaction cylinder to make sure that you're inducing the reaction. And as I talked about, the air bearings are actually helping us to create a cushion of air to move, to translate us back and forth. So there is a chance for the reaction to bypass. But we introduce, graphite seals, we call them rings, on the piston head. So it actually seals that pressure. And those graphite is not causing wear and tear on the equipment itself, but it wears itself down over time as you're operating more. It's susceptible to pressure and temperature. So over time, it just wears down. And that's our biggest consumable. In terms of how often do we maintain those, it depends on the duty cycle of the system and the run hour. So whether running full load, whether running 100% of the time, the duration changes. But we'll be more than happy to address specific questions. But it's somewhere between roughly 500 to 800, depending on the equipment. Again, those are really relatively simple to change. They're just kind of like, we're actually, you could just open the package. Relatively, a certified HVAC technician can be trained on it. Those seals can be easily changed within 2 hours, and this equipment is back up again.
Okay, thanks. Another question regarding the fuel blends in Xendee. The question is, if Xendee can support fuel blends, and yes, we can do this. You can even define your own energy content for fuels. And I think this is the main reason why we also work together, as Shah said, because we can model these different fuels in Xendee for Mainspring here. We have only 2 minutes left, so I think, okay, wait a minute. Where is it? There were not so many questions that I lost track, so I cannot find it anymore. Okay, I think it's gone here. So I think we're good on this. There's a lot of redundant ones. So I think, yeah, in terms of derating, because I think it's a combined question. If we can model technology derating in Xendee, but is there also a kind of derating on your side in terms of power output or no?
Yeah,
that you see over time or no?
Yeah, over time, no, it's not, no, there's no derate over time. This is not like a fuel cell where you degrade over time. There's no derate over time. We only derate because of altitude and temperature. And obviously, temperature, you need to account for it because that's a derate throughout the year. But even with derates with temperature, we're actually doing pretty well. I mean, there's relatively no derate until pretty elevated temperatures, which is typically seen across the industry. The only derate that we start to see is when you get up into high elevation. Again, we can obviously share numbers once we have a project to work with. We have MOU, and you'll be surprised that we actually compete with proven technologies like, for example, diesel genset or natural gas genset pretty well when it comes to derates. So these are not like susceptible to temperature and elevation that much. Yep.
Okay, so I think I want to leave it here because we only have 1 minute left, and I really want to thank everyone for participating in this very lively discussion and webinar. I personally enjoyed it a lot because it's a cool technology. And as I said, just reach out to Mainspring or us if you're interested in modeling the technology, or if you need some support. And we will go through all the questions here that we received and check if we answered them or if there's some remaining ones, and we'll follow up. And by the way, the webinar is also being recorded, and I think we'll share this later on and send out a kind of link for this. So with this, I really want to thank everyone. I want to thank Mainspring Shah for this really cool webinar.
Thank you, Michael. Thank you very much. I also want to thank everyone for sitting through our presentation. Again, any questions, we'll be more than happy to answer. Have a good one. Take care.